Good morning, students. Yesterday we discussed the examples of Hilbert spaces, and today we will discuss the examples of vector spaces which are not inner product spaces and hence not the Hilbert spaces. So in order to discuss the examples of such spaces, we require a lemma which is called parallelogram equality. So what is parallelogram equality? A norm of the inner product space satisfies the parallelogram equality given by x plus y norm square plus x minus y norm square is equal to 2 times x norm square plus y norm square. In geometry also we studied that the sum of squares of sides of a parallelogram is equal to sum of squares of the diagonals of the parallelogram. Here x plus y norm, this is the length of one of the diagonal of a parallelogram, and x minus y norm, that is the length of diagonal of parallelogram, and x norm y norm, this represents the lengths of sides of the parallelogram. So we can say that the sum of squares of sides is equal to sum of squares of diagonals. So this equality, this is known as parallelogram equality. So let us prove this equality. So in order to prove this, let us consider x plus y norm square. Now by definition, x plus y norm square means inner product of x plus y with itself. Now by using the first property of inner product, linearity property with respect to the first variable, this can be written as inner product of x with x plus y and inner product of y with x plus y. Now again using the property of conjugate linearity with respect to second variable, this can be written as inner product of x with x plus inner product of x with y plus inner product of y with x plus inner product of y with y. Now inner product of x with x means x norm square, inner product of y with y is y norm square. So we have x plus y norm square is equal to inner product of x with x plus inner product of y with y plus inner product of x with y plus inner product of y with x. This is actually x norm square and this is y norm square. Now we are to find x minus y norm square. So in order to find that, we can replace y by minus y in the equation 1 here. So from here we get, this will remain as it is, inner product of x with x, inner product of minus y with minus y plus inner product of x with minus y plus inner product of minus y with x. Now again we can write this term as inner product of x with x minus inner product of y with minus y minus inner product of x with y minus inner product of y with x. Now again using the properties of the inner product, this can further be written as, if we take a scalar outside from the second variable, then that will become conjugate. So here if we take minus 1 outside of the inner product, we get minus 1 conjugate, but that is a real number, so its conjugate will be same as itself. So this can further be written as inner product of x with x plus inner product of y with y minus inner product of x with y minus inner product of y with x. Now adding the two equations, equation 1 and equation 2, we get x plus y norm square plus x minus y norm square is equal to 2 times inner product of x with x plus inner product of y with y. Now inner product of x with x, that is x norm square, and inner product of y with y, that is y norm square. So we have proved that the sum of squares of diagonals is equal to the sum of squares of the sides of parallelogram. That is why the name parallelogram equality is suggested. Here we can show it geometrically also. We have shown a parallelogram. X and y are the adjacent sides of this parallelogram. This is vector x, this is vector y. The length of this side will be x norm, then length of this side will be y norm, and this length denotes x plus y norm, and this denotes the length of another diagonal which is x minus y norm. So this result is used to prove that a inner product space which does not, a space which does not satisfy parallelogram equality is not inner product space. So if a norm does not satisfy parallelogram equality, then we can say that it cannot be guaranteed by, it cannot be generated by an inner product. and such norms exists. Let us see the examples. So the first example of the space which is not inner product space is LP space. The space LP with P not equal to 2, equipped with the norm x norm is equal to summation xii mod raised to the power p whole raised to the power 1 by p. This is the norm in LP spaces. Here p varies from 1 to, and that is finite. P is not equal to 2. Here we will prove that this space LP is not inner product space, and if it is not inner product space, then it cannot be Hilbert space. So in order to prove that it is not inner product space, we will prove that the norm is not induced by any inner product. For this we prove that it does not satisfy the parallelogram equality. So in order to show it, let us consider two elements x and y from the space LP. So let us take x is given by the sequence 1, 1 and all the other members of the sequence as 0, and y another sequence which we have taken 1, -1 and all the other coordinates 0. So we have taken two elements x and y from LP space. Now let us find the norm of x. Now by using the norm definition in LP space, this will be given by exile 1 mod raised to the power p plus exile 2 mod raised to the power p and so on, whole raised to the power 1 by p. Now what is exile 1? 1. Exile 2 is 1. All the other are 0. So putting the values here, we get 1 plus 1 whole raised to the power 1 by p. So we get 2 raised to the power 1 by p. Now let us find y norm. Now y norm means 1 mod raised to the power p plus -1 mod raised to the power p and so on, and whole raised to the power 1 by p. Now this is 1, and this -1 raised to the power p depends upon p. If p is even, this will become 2 raised to the power 1 by p. If p is odd, this will become 0. Now let us find x plus y and x minus y. So adding x and y coordinate wise, x plus y will become 2, 0, 0, 0 and so on, and x minus y, in x minus y only the second coordinate is 2 and all the another coordinates, those are 0. Now let us find the norm of x plus y and x minus y. Now x plus y norm. So x plus y norm, again by using the definition of norm, this will be 2 raised to the power p plus, because all the other coordinates are 0, so that will become 2 raised to the power p and whole raised to the power 1 by p. So x plus y norm, that is 2. Now x minus y norm, because in x minus y the second coordinate is 2 raised to the power p and all the other are 0. So x minus y norm will be, in x minus y the second coordinate is 2, all the other coordinates are 0. So by definition of norm, x minus y norm will be 0 raised to the power p plus 2 raised to the power p and so on, whole raised to the power 1 by p. So we get x minus y norm is equal to 2. Now let us check that whether parallelogram equality is satisfied or not. Now parallelogram equality is x plus y norm square plus x minus y norm square is equal to 2 times x norm square plus y norm square. Let us put the values of x plus y norm, x minus y norm, x norm and y norm. If we put the values, we can see that on the left hand side we get 8, but on the right hand side we get 4 into 2 raised to the power 2 by p. Now 4 is cancelled from both sides and we get this term. Now because base is same, so powers must also be same. So we get p 2 by p is equal to 1. From this we get p is equal to 2, but p is not equal to 2 here. So we can say that parallelogram equality is not satisfied if p is not equal to 2. So we can say that LP space with p not equal to 2 is not a Hilbert space. So this was one of the examples of the spaces which is not Hilbert space. Now we discuss one more example of the space which is not Hilbert space. The space CAP, the space of all the continuous functions defined on the closed interval AP. In this space we define the norm by this definition: x norm is equal to the maximum of mod of x, where this t belongs to the closed interval AB and x is the element belonging to this space. We will prove that in this space parallelogram equality is not satisfied, and hence this will not be inner product space and hence not a Hilbert space. So in order to prove that this is not a Hilbert space, let us check that the norm defined by this term cannot be obtained from the inner product. So in order to satisfy it, let us take two elements x and y belonging to the space CAB. So first we have taken 1 because 1 is constant, so it is continuous function on the closed interval AB. And second function we have taken polynomial function divided by polynomial means rational type function for every t belonging to closed interval AB. Because these two are continuous functions, so they belongs to the space CAB. Now let us find the norm of x and y. Now the norm of x means norm of 1, that will be 1, and y norm means, by definition of norm, this is the maximum of mod of t minus a upon b minus a. Now this expression will be maximum when t is equal to b. So if t will be b, so this will become b minus a upon b minus a, means we get 1. Now let us find x plus y and x minus y. Then their norm, x plus y is 1 plus t minus a upon b minus a, and x minus y is 1 minus t minus a upon b minus a. Now let us find their norms, x plus y norm. So firstly, x plus y norm means the maximum value of mod of this expression. Now because its maximum value is 1, so 1 plus 1, so maximum value of this expression will be 2. It means x plus y norm is 2. Now let us find x minus y norm. Again, by definition of norm, this is the maximum of x minus y mod. Now substituting the values of x and y and taking LCM, we get x minus y norm is equal to the maximum of b minus t upon b minus a norm. Now this value will be maximum if t is equal to, if this will become a. So b minus a upon b minus a mod, that will give 1. Now let us put these values in the parallelogram equality. Now by definition, parallelogram equality is x plus y norm square plus x minus y norm square is equal to 2 times x norm square plus y norm square. Now x plus y norm is 2, x minus y norm, that is 1. So substituting the values on the left hand side, we get 5. On the right hand side of parallelogram equality, 2 times x norm square plus y norm square is equal to 2 times x norm is 1, y norm is 1. So putting the values, we get 2 into 2. So that becomes 4. Thus we can see that these two sides are not same. So it means parallelogram equality is not satisfied. Thus we can see that the norm defined by x norm is equal to the maximum of mod of x does not satisfies parallelogram equality. And if parallelogram equality is not satisfied, the space is not inner product space. And if a space is not an inner product space, then it cannot be a Hilbert space. So these were the examples of the spaces which are not Hilbert space.